It's really good. Make sure without fail you have to submit all your test notes and classwork within this week. Okay. Please aware of this. Next week onwards, the classes will be starts regularly. Then also we will conduct the exams. So don't believe any rumors and don't believe any other circumstances around your area. Okay. So listen. This week we already saw about that electrostatics. What is the electric field and electric field lines, and then Coulomb's law, everything. Okay. This week we wanna discuss about electric flux and applications of Gauss law. So what is the electric flux? What is that? Electric flux. The electric flux is nothing but consider there is only one charge. There is a lot of electric field lines passing away from the positive charge, right? The positive charge is always pointing away. If I have the two type of areas, one is the A, let A be the one of the area and B be the one of the area. See how many electric lines are passing through A? 2. How many electric field lines passing through B? Is only 1. So the electric flux on A is more than that electric flux of B. Okay, so the electric flux is nothing but pi E, denoted by letter pi E is nothing but number of electric field lines, passing through the given area, So pi E equal to Ea cos theta. Ea cos theta is a scalar quantity. So if you want to remove that, you have to, it is a dot product. Okay. So Ea cos theta. When theta equal to 0, that means there is a lot of electric field lines. Okay. There is a lot of electric field lines. Have the play sheet. I have the one area. Area. Here, if I am keeping this area like this, the normal parallel to the area. Look at this picture. N will be here. The normal parallel and anti-parallel to this area. That means when the theta equal to 0 degree, normal 0 degree is parallel towards the electric field lines, then pi E equal to Ea. So maximum electric flux will be there. When that's electric field lines, I have the sheet like this, I have the area like this, the normal perpendicular to that electric field lines, then theta equal to 90 degree, then electric flux will be equal to 0. When the electric flux will be equal to 0? When the normal perpendicular to that electric field lines. Okay. Now, suppose if I have the charge in an enclosed surface. Okay, remember that the electric flux is nothing but number of electric field lines passing through that given area. It is a scalar quantity. So what is the SI unit for electric field? Newton Coulomb inverse per area meter square. The SI unit of the electric flux, Newton Coulomb inverse meter square. Suppose I have the one small sphere. Here I have the charge. I don't know what is the electric field enclosed in the surface. How can I find that? Pi E equal to Ea. Correct? Pi E equal to integral surface over integral enclosed surface. Integral over is nothing but integral enclosed surface. So E is a constant, take it outside. dA will be there. Okay. E dA cos theta. So now, what is the area of the sphere? We know that electric field Q by 4 pi epsilon naught r square. What is the area of the sphere? 4 pi r square. So 4 pi r square will be cancelled. So the total electric flux in an enclosed surface will be equal to Q by epsilon naught. The total electric flux in an enclosed surface will be equal to arbitrary Q by epsilon naught times. It is given by Gauss law. He is a great scientist, and also remember that pi equal to Q by epsilon naught. Okay. So okay. One of the main applications, there are the 3 applications of Gauss law. The first one is the electric field due to the applications of Gauss law. Okay, it's very important. 5 more questions. Applications of Gauss law. Now, The electric field, first one, the electric field due to an infinite long straight charged wire, long straight charged wire. Now I have the one charged wire which is have only positive charges and which is have the positive charges. The positive charges always pointing away. Positive charges are pointing always away. I can draw the imaginary curved line on the surface of that. So this one will be called as Gaussian surface. This one we called as Gaussian surface. What is that Gaussian surface? The imaginary curved line drawn on the surface. Imaginary curved line. It's an imaginary line drawn on the surface. It is called Gaussian surface. Here we got top surface, bottom surface, and curved part. This look like a cylindrical shape. See, this look like a cylindrical shape. Top surface, bottom surface, and curved part. Okay. So now listen. We have to find or we have to prove phi equal to Q by epsilon naught. From here, from the Gauss law, we have to find what is that electric field due to an infinite long straight charged wire. So first we have to find what is the pi. The pi will be equal to integral over EDA. Integral over EDA. So okay, what is the integral over EDA? So E is a constant, take it outside, integral over dA. Okay, so E integral over, here we have three parts, correct? First one is integral of EDA top surface plus integral of EDA bottom surface plus integral of EDA curved part, curved surface. Now the top and bottom are same in magnitude but opposite direction, so they will cancel each other. Only the total electric flux will be equal to integral EDA of curved part. Got it? Now, what is an integral EDA? Will be equal to E is the constant taken outside, integral of dA. What is the area of the cylinder? It's nothing but 2 pi RL. 2 pi RL. So this is your integral EDA. Now, the next one. This is nothing but phi E. Okay, phi equal to E 2 pi RL. Now, Q by epsilon. We have to find what is the Q. Here we have to introduce one new concept, lambda. Lambda is nothing but linear charge density. Lambda is nothing but linear charge density. Charge per unit length. Charge per unit length. From here we can find what is the Q. Q equal to lambda L. That's it. Now substituting here, pi, what is the pi E? So pi is nothing but E 2 pi RL will be equal to lambda L by epsilon naught. Lambda L by epsilon naught. L will be cancelled. So E will be equal to lambda by 2 pi R epsilon naught. Lambda equal E equal to lambda by 2 pi R epsilon naught. This is the electric field due to an infinite long straight charged wire. When lambda is greater than 0, the electric field will be pointing outward. Pointing outward. When lambda is lesser than 0, it's always pointing inwards. Pointing inwards. Okay. So first we have to draw what is that charge. Okay. This is a R, and you can write the electric field will be acting like this. Okay. You can draw whatever maybe you have. Now listen. There is a top surface, bottom surface, and then curved part here. So the total electric flux will be equal to curved part alone. So E 2 pi RL is nothing but area of the cylinder, and pi will be equal to E 2 pi RL. From here we can find what is the surface charge density. Surface charge density is nothing but charge per unit length. So Q equal to lambda L. So from here we can substitute and get the answer. Okay. E equal to lambda by 2 pi R epsilon naught. And I gave some important questions, question paper, that board exam question paper, and also answer key to Aisha Siddhika. Get it from her. Okay. Collect it and then see how the answers keys will be there. Okay, and also note the important things. Next, the second one, electric field due to an okay, due to a charged plane sheet. Due to a charged plane sheet. It's like a plane sheet. Okay. Here I have the plane sheet, which is charged. Positive charges are on the surface of the plane sheet. Is pointing away. P dash. Here also we have to find what is that pi equal to q by epsilon naught. Pi equal to q by epsilon naught. Now listen. Here also p and here also p dash. Okay, it's like a plane surface. It's always pointing away from the surface, and here also away from the surface. Okay. And what is the pi? Pi will be equal to integral over EDA. Integral over EDA. Here we have the two parts, P and P dash. So integral over EDA will be equal to integral of P EDA plus integral of P dash EDA. So here area is area. Okay, DA is nothing but here EA plus EA. I can write 2EA. 2EA. This is your pi electric flux. Now here I am also again the new concept sigma. Sigma is nothing but surface charge density. Lambda is nothing but linear charge density, and here sigma is nothing but surface charge density. So surface charge density is nothing but charge per unit area. Charge per unit area. Then Q equal to sigma A. Then Q equal to sigma A. So substituting an equation. So pi, what is the pi? 2EA will be equal to sigma A by epsilon naught. Sigma A by epsilon naught. So A will be cancelled. So E will be equal to sigma by 2 epsilon naught. Sigma by 2 epsilon naught. Now listen. This is the electric field due to an infinite or charged plane sheet. Charged plane sheet. Now electric field due to the two parallel charge infinite sheets. Two parallel charge infinite sheets. Same. For the single sheet you can get sigma by 2 epsilon naught, right? If I have the another charge sheet like this, okay, here also I have the charge. Here also is pointing away. Here also is pointing away. At this point it will become 0. Okay, inside the point will be 0, but outside the point. So what will happen here? Only this point and this point will get pi will be equal to sigma by 2 epsilon naught. Sorry. The total electric field will be equal to sigma by 2 epsilon naught due to this charge sheet plus sigma by 2 epsilon naught due to this charge sheet. So 2 of sigma by epsilon, 2 epsilon naught. So 2 will be cancelled. The total electric flux due to the two charged plane sheet will be equal to sigma by epsilon naught. Sigma by epsilon naught. That's it. So this is due to the single charge sheet, and this is due to the plane charge sheet of 2 or multiple, whatever may be. Okay. So next one. These are the plane charge sheet, and then if the point electric field due to then uniformly charged spherical shell. Uniformly charged spherical shell. Uniformly charged spherical shell. I have one spherical shell, which is to have the positive charges on the surface, and have the point here. First, it's lies outside that point, outside the shell. Okay, the point which is acting outside the cell. We know that E equal to Q by 4 pi epsilon naught R squared. Correct. So here I have the R, which is called radius, and here, okay, we have the radius R. The point will take as capital R. Okay. So when it lies outside the point, it's across the radius. So we can write capital R square. That's it. When it lies on the surface, the point lies on the surface. What happened? Lies on surface. We can write E equal to Q by 4 pi epsilon naught R square. Because this is it's outside the cell and this one is on the surface. Now, if the point inside the cell will be equal to 0 because there is no electric field inside the charge. See, there is no electric field act inside the point. Okay, now listen, take the page number 46. The electric field due to the uniform charge is equal to 0 at all the points inside the cell. Okay. Gauss law is powerful technique whenever the given charge configuration possesses a spherical, cylindrical and planar symmetry. Then the electric field due to such a charge configuration can be easily found. If there is no such a symmetry, the direct method, Coulomb's and calculus method can be used. Conductors at electrostatic equilibrium. There are 4 types of electrostatic equilibrium. There is 4 types of electrostatic equilibrium. Turn page number 45 and mark all the 4 points. Okay. Electrostatic equilibrium. Electrostatic equilibrium. So first one. The total electric field is 0 wherever inside the conductor. So first point, inside the conductor. Okay, inside the conductor, if I have the point, then the electric field will be equal to 0. The total electric field will be 0 everywhere inside the conductor. The second one, there is no net charge inside the conductor. The charges must reside only on the surface of the conductor. Okay, if you have the conductor, the charges only must be on the surface of the conductor, not inside. Lever lies on the inside the surface. It only the surface of the conductor. Third point. The electric field outside the conductor is perpendicular to the surface. The electric field outside the conductor is always perpendicular to the surface, which is equal to sigma by epsilon. That means depends upon the surface charge density. The fourth one. The electrostatic potential will be same everywhere. Okay, electrostatic potential will be same value on the surface inside and outside the conductor. So whatever may be, here I have the surface and here I have the surface. So inside and outside of the surface, the potential will be same. Okay. So third point, sigma by epsilon naught, which is equal. Okay. Next one thing. You know what is that? Electrostatic shielding. Do you know what is that electrostatic shielding? Electrostatic shielding was first discovered by Faraday. It is well known by Faraday cage. You know that from this movie, Faraday cage, which is never conduct any electricity inside that Faraday cage. It's microwave oven. Now, if you have the conductors, Faraday did this experiment by himself. What he did, he surrounded himself by the it's like a jail. Okay, it's like a jail, a prison with iron rods, and then he went inside and then he passing all the electric field around that iron rod. When the lightning striking, it never attracted by that iron rod because there is no electric field. It's never attracted by himself by lightning. Okay, so why? Because the electric field inside that person, electric field inside the conductor will be 0. So it is an iron rod fully surrounded with the electric field. When the lightning striking is never attracted by himself because the electric field inside the conductor. The human is a good conductor, but he is inside that electric field, so the lightning does not strike on him. Okay, so it is also works on the principle of electrostatic shielding in the car or bus. When the light striking during the lightning, whether it's safer inside the car than tree. Okay. When the person standing under the tree and the human earth is a good conductor, so they will attract that lightning, so strike on the human. Same person when he's sitting inside the car, inside the car, what will happen? The metal body of the car provide electrostatic shielding. Metal body of the car provide electrostatic shielding. So when it's striking, it provides electrostatic shielding. It covers and it receives all the lightning and passing through the earth's surface through the tires or the metal body of the car, and provide the Faraday cage also. The electric field inside the conductors inside the conductors will be equal to 0. So it will provide as the electrostatic shielding, and also it works on the principle of electrostatic equilibrium. Electrostatic equilibrium. The total field, electric field inside the conductor, the metal body of the car is a good conductor, right? So metal inside the conductor, the electric field will be 0. Okay. Now the next one is electrostatic induction. We can produce charges by 3 methods. First one, by friction, by conduction, by induction. Friction, conduction, induction. So what is mean by electrostatic induction? Electrostatic induction. Now I have one conductor which is a metal sphere. I have one metal sphere. There is a uniformly spreading of the both positive and negative charges inside the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, uniformly both it's a neutralizer. Okay, so both positive and negative charges will be present inside on the surface of the metal sphere. Now I am bringing another metal rod or charged rod with the negative charge, negatively charged rod near to that metal. What will happen? All the positive charges will be attracted towards this rod, and the negative charges will be repelled away. Now I can earthing these negative charges into the ground. Grounding these negative charges inside the ground. What will happen? All the negative charges will be grounded. Now I can remove this rod also. What will happen? The metal will become uniformly spread over metal rod will have only positive charge which is uniformly spread out the metal. So producing charges without any contact. Producing the charges without any contact, it is called electrostatic induction. It is called electrostatic induction. Charging without actual contact is called electrostatic induction. Remember that. Producing the charges without any contact is called electrostatic shielding. And turn page number 51, dielectric and insulator. Okay, what is mean by dielectric and what is mean by non-dielectric or non-polar molecules and non-polar molecules? The polar molecules. Okay, dielectric means it's partially electric. Okay, it's partially conduct. It's like a semiconductor. Okay, but here there are two types. One is the polar molecule, and then the another one is non-polar molecule. Okay, so what is mean by polar molecule and non-polar molecule? The positive and negative charge. Okay, for example, turn page number 51. A non-polar molecule is one which the centers of the positive and negative charges coincide. The positive and negative charges will be positive and negative charges will be coincide with each other, coincide with the center of gravity. Charges coincide with center of gravity. Center of gravity. For example, H2, N2, CO2. These are the best example for H2N2 CO2. These are the best example for non-polar molecules. They have the permanent dipole, and also they have the they have the permanent dipole, and they have the permanent dipoles moment. Polar molecules. In polar molecules, the center of the positive and negative charges are separated even in the absence of electric field. So in the absence of electric field, the positive and negative charges will be separated. They never coincide with the center of gravity. Now, in the absence of electric field, they have the permanent dipole, they have the permanent dipole. They will align themselves. They align themselves. Here we have the examples of N2O, H2O, HCl, NH3, ammonia, all those things. What are the dipoles? Dipoles. The best examples are dipoles. So these are dipoles which have the permanent dipole moment. Here they don't have any permanent dipole moment. When the presence of electric field, they will move in a random manner in absence of electric field or external field. When they apply the electric field, they align themselves in a particular direction, act as a dipole, and that time they have the dipole moment, that temporary dipole moment they have at the time. So this is called induced dipole. In the absence of electric field, the non-polar molecules act. They don't have any dipole moment. In the presence of electric field, the non-polar molecules act as a dipole. They producing dipole moment. That moment we called as induced dipole moment. So what is that? Polar molecules and non-polar molecules. Only two more questions. The positive and negative charges separated by and they never coincide with the center of gravity. In the presence or absence of the electric field, they providing the dipole moment. They have the permanent dipole. They act as a dipole. In the absence of electric field, they are non-polar molecules. They don't have any permanent dipole. In the presence of electric field, they act as a dipole and they have the permanent dipole. That is called induced dipole moment. So this is enough for this week. Next week, inshallah, we'll discuss about that capacitors and capacitance. So remember that. What is that electric flux? Electric flux is nothing but what? The total electric field lines passing through that given area, EA cos theta. And what is the Gauss law? The total electric flux in an enclosed surface will be equal to Q by epsilon naught. And the applications of Gauss law is very important. Two applications are very important. First one is the infinite long charged wire. The second one is charged plane sheet. And then the spherical shell. After that, what is that? Electrostatic induction. Producing charges without any contact. After that, what is dielectric? Dielectric is nothing but the partially electric conductivities. And then they have the two types, polar molecules and non-polar molecules. The polarization. What is meant by polarization? The total dipole moment per unit volume of dielectric. Total dipole moment per unit of the total dipole moment per unit volume of dielectric. So inshallah next week we will see the capacitors and capacitance of the capacitors. Okay guys, thank you. Allah Hafiz. Submit your test note, classwork without fail. This is my request. That's it. Thank you guys. Allah Hafiz.